Welcome everyone to the third seminar in the Indus seminar series. Let me introduce today's speaker, Richa Naja Jain. She is a PhD candidate at the Space Physics Laboratory of the Indian Space Research Organization ISRO in Trivandrum, India. She works in the Radio Science and Ionosphere Modeling Division under the supervision of Dr. Rajkumar Chaudhary. Her doctoral research focuses on studying solar coronal dynamics and its impact on the coupled magnetospheric ionospheric thermospheric system over the Indian low latitude ionospheric region. She holds a bachelor's and master's degree in physics from the IISc Bangalore, and also, interestingly, she has a master's degree in history from Indira Gandhi National Open University, India. With that, I would like to invite Richa to the seminar. Richa, please go ahead.
Hi everyone. Thank you, Gauri, for the nice introduction. And I'm also grateful to Indus for giving me this opportunity to share my work with you all. So here I will be presenting my work. And the topic which I'm talking about today is the active remote sensing of inner and middle solar corona. I'm a PhD candidate, currently in my 4th year and working with Dr. Rajkumar Chaudhary in SPL, BSSC, Trivandrum, India. So as all of us know that sun is at the heart of our solar system, and it not only gives us heat and light, but it also it also radiates a lot of energetic particles and the magnetic field, which creates interesting impacts on the near Earth and near planetary environment. So the outline of my talk will be, I'll tell you a story of an arcane crown and a ubiquitous wind, and how this poses an enigma for any heliophysicist. And there is a very ingenious technique in which we use the radio messenger to try to answer our queries and find the solutions. And two very interesting experiments which were conducting by the spacecraft, which are actually the planetary missions, but they helped us to study the solar physics as well. So here I'll start my talk. So first of all, okay. So what is solar corona? Corona is the outer atmosphere, which is consists of a plasma of any star. It is very feeble, it has a very low density, and it is observed mostly during the solar eclipses because of the emission caused by the light which has been scattered by the electrons. Now, this is not a very simple structure. When you see it, you will find that there are a lot of interesting features on it, such as bright arcades, helmet structures. Sometimes they appear darker coronal holes, there are filaments, prominences. And also this corona does not have a sharp boundary. It gradually fades into the solar wind and into the interplanetary medium. Now the solar wind. Solar wind is the continuous flow of ionized solar plasma and the magnetic field that pervades the entire interplanetary space. Because of the properties, it also carries the frozen in magnetic field, and it creates and carries the magnetic field from the sun's interior into the entire cavity, which is carved as a heliosphere. Now, there is a very interesting thing. There were a lot of the story of discovery of solar wind is very interesting. First of all, it was a solution of a mathematical equations given by the Parker. Parker called the corona as a hydrodynamic corona in 1958 in one of his paper, which was purely based on mathematics. Now, I would always like to drop an anecdote here. The anecdote goes by this: the Parker sent his paper to the editor of ABJ, and two renowned editors rejected his paper. Except for that, Chandrasekhar was the editor at that time, and he could not find any flaw in the mathematics, and he accepted that paper. This was the era when the space-based explorations have still not begun. So this is the beauty. I really appreciate the beauty of mathematics in the study of science. So, okay, so just a small anecdote. And now when we started sending our spacecraft into the like outside the Earth's atmosphere, they all detected the flow of charged particles at all the time. This confirmed that this flow is ubiquitous. And also there was another spacecraft which did a very daunting thing of slinging outside the ecliptic plane. It observed these charged particles even at the higher helio latitudes. So this flow was observed at all the time at all the helio latitudes. This created a very interesting study of how this particle flows away from the sun all the time. Now, there is a very interesting question. I have introduced the outer atmosphere is corona, and the particles which flow are the solar wind. The natural query arises, where is the boundary? Like, how do you separate which is the corona and where does the solar wind flows? Scientists have proposed an imaginary locus of the point, which is called as Alfvén surface, which is a boundary separating the corona from the solar wind. It is a place where it is assumed that the coronal plasma has achieved the velocities greater than a certain speed, which is called as Alfvén speed, so that they will not flow back into the, they will not fall back into the solar atmosphere, and still they will carry, they will be accelerated to the higher velocities, and they will be carried forward in the interplanetary medium. There is a very interesting, and it was always an ongoing research how to define the boundaries of this Alpine surface. As my talk will proceed, you will see that this is not a very strict sphere or anything. The boundaries and this locus of the point keeps on continuously changing with respect to the emergent features on the solar surface and with the solar cycle. So, and also, as you know, the study of solar wind is quite important because it creates a lot of interesting space weather events in the Earth, near Earth environment and other planetary systems as well. So now the solar wind near the asymptotic values, there were two kind of flows which were observed in the solar wind. They are known as slow solar wind and the fast solar wind. Slow solar wind are the ones which were the further observation. They were said to originate from the equatorial latitudes, mostly equatorial and low equatorial latitudes. They are highly variable, they have a lot of turbulence, and their flow speeds are relatively smaller. Their asymptotic flow speeds are relatively smaller. They have higher densities. Now, there were another kind of flow speed which was observed. They were termed as fast solar winds. Their origin were mostly found from the coronal holes. Coronal holes are the patches which appear darker in the UV images because they consist of the particles which have relatively lesser densities, although they are the places where there are open magnetic field lines and the stronger magnetic field lines, and they usually carry the variations in those field lines and the particle regions are usually smaller. I'm dropping these introductory part because in the later in the talk, when we are going to compare our results from the two different phases of solar cycle, there will be some lot of interesting things about the observations of these two different type of flow particles. Now, I'll talk about some interesting things which were happening. Because a scientist, they studied from the spectrographic things, they found that the photospheric temperature is approximately 6,000 Kelvin. And the coronal temperature, which is the outer atmosphere, the temperature is in million of kelvins. Just imagine a person, a heliophysicist, for example, sitting near a campfire. As you move away from the campfire, your common observation says that the temperature should decrease. But in our solar case, exactly reverse was happening. So this gave rise to a natural query, like coronal heating problem. What are the mechanisms which are creating this kind of high temperature increase? So one of the logic that proposes, let's suppose there is some mechanism which is directly bringing the heat from the inside and dumping it the outside, so that the outer temperatures are also as high as the inner temperatures. So with this simplest assumption, with the simplest explanation and anecdote, there were two plausible mechanisms which are now suggested for the heating of the solar corona. First one is heating by the MHD waves and turbulence. This theory assumes that there are a lot of, because of the stronger magnetic fields of the solar corona, there are a lot of waves, magnetodynamic waves, which are propelled outwards from the photosphere into the chromosphere and then into the inner and the middle, in the lower coronal region. There they interact with the particles such that because of the turbulence, the dissipation of the energy happens. The magnetic energy contained in these waves dissipates in the medium, which increases the temperature of the medium, and which finally translates into the higher velocities of the particle. There is another line of thought which has also been observed. These are the transient or the small scale impulsive energy releases during the nanoflares and the emissions. So first thing is what causes the high temperature of the solar corona, and what is the impact of this high temperature of the solar corona? So Parker gave an approach in which he assumes that there is because of this high temperature if we assume a high temperature of solar corona and we solve the simple hydrodynamic fluid equations, but including gravity as well as the pressure gradient force, we will find certain kind of solutions of the particle flowing out of the coronal medium. And here I presented, there is a small graph about the topology of different solution for the Parker equation. One solution says that there will be a certain flow of particle which will start near the coronal solar corona as subsonic flow. After a critical point, it will start getting accelerated and it will become a supersonic, and beyond which after a while there it will assume the asymptotic values. These asymptotic values are the one which we observe in the near Earth environment. So in the near Earth area, so near corona, the flow is actually subsonic and sub-Alfvénic. Somewhere a transition happen in which the flow the solar wind is accelerated, the particles are accelerated, and they do the transition from the subsonic to the super-Alfvénic and supersonic velocities, and after that they are carried forward. So the proposed mechanism, which is very prominent one, is the turbulence turbulence in the MHD waves causes this heating, which mostly occurred in inner and middle corona, that give rise to the high temperature, and this further propels the solar wind particles. So, yeah. Okay, so now I will focus on what are the various types in which we can observe the corona and the solar wind. First thing is, when our study started, it started with the ground-based solar observatories. But as you know, there are limitations of the optical window because of our atmosphere. We cannot observe the solar emissions in all the wavelengths. So to solve this, our problem was solved when the space age started, such that we can park, lot of spacecraft were parked at the L1 point, such as SOHO, ACE, and or Aditya L1 is also recently is there, and they could conduct the studies of the sun and the particles. But all of this was happening from very far. To actually know what is happening in the actual region, it is the best thing is to conduct in-situ measurements. But these are really daunting missions, and so far only 2 missions have been launched and the proposed. So far only 2 missions are there which are trying to conduct these kind of daunting missions. What is the another ingenious and the simple solution to this problem? So this technique is known as the remote sensing technique comes to our help. So what happens? Let's just, instead of going directly there and studying the thing, let's just ask a signal which is traveling through that medium. What did you observe in that place? This is simple. In the simple way, we explain the remote sensing technique. So remote sensing can be carried out with the signals which are generated naturally within the coronal region, or the signals which are from any natural resource such as a galaxy or a pulsar which are radiating the solar wind, or a spacecraft when they are in their solar conjunction trajectories. So in the coming slides, I'll explain what are the solar conjunction trajectories and how this technique is used. Solar conjunction. So what is a simple solar conjunction event? Solar conjunction is just a term whenever there is a celestial event such that a planet, spacecraft, or any solar system object is on the opposite side of sun than from the Earth. So in this case, whatever radio transmission is happening from the spacecraft, it will obviously pass through the solar corona, and then it will be received at the ground station. Now, because of the properties of the propagating medium, the received signal will absorb some inherent signatures, and those signatures will be used to study the property of the medium. And actually, these solar conjunction events are not some very mundane events. They have given us a lot of interesting science in the past, such that in 1975 there was a spacecraft Mariner which was under this solar conjunction trajectory, and it helped us actually to verify the Einstein GR theory because of the Doppler shift in its signals, which was happening because of the curvature, space-time curvature. And Ulysses also used this kind of conjunction event to study the flow across the solar poles. Now, what is actually this technique is? This is here in this schematic, you can see it's a very simple technique in which a spacecraft, when it is on the opposite side of sun, whenever it will send a signal, the signal will traverse, it will have a single traversal of the solar corona before reaching the ground station. Now you know that the solar corona is an ionized medium and it has an inherent turbulence. Because of the turbulence, there will be some dispersion effects which will be produced in the frequency of the received signal. There will be some frequency dependent effect, there will be some Doppler shifts. So now there will be 2 kinds of Doppler shifts. One Doppler shift which is labeled as a geometric Doppler shift, which will arise because there is a relative velocity because there is a relative velocities between any spacecraft and ground station which is located on the Earth, which is also revolving. Now there is another kind of dispersion effect or the Doppler shift which will arise because of the fluctuations in the density or the refractive index of the medium. Here our medium is the turbulent coronal medium. So we can use the spectrum of the received frequency fluctuations to actually indirectly explain the turbulence which is happening in the medium, and this density turbulence will help us to associate the properties of the particles and their motion which is creating the turbulence. So this is basically the idea about this very simple and very ingenious technique which help us to probe the what is the interesting phenomena, a lot of complex phenomena happening at the solar corona without actually doing the in-situ measurements. And also this is a very interesting way because when the in-situ measurements are conducted, our remote sensing measurements give they help to support the observations of those measurements. So now I have come to the interesting part of actually two very interesting experiments which are conducted by the two spacecrafts, which are basically the planetary missions. So first one is our Indian mom, which is adoringly we call it as a Mangalyaan mission. So this mission, this is India's first interplanetary mission. It was launched on November 5th, 2013, and it was injected in the Martian orbit in 2014. Now, because of the relative orbital period of Mars and the Earth, which is approximately 2 years, every 2 years, this kind of conjunction event happens when Mars is on the opposite side of the Sun than the Earth. And during that time, any spacecraft which is revolving around Mars, if it will send a radio signal to the receiver at the Earth, the radio signal will bound to pass through the coronal medium. So scientists at the ISRO planned this opportunity, which occurred in May and June 2015, to conduct the coronal radio sounding experiments. And then the data was shared by the ISTRAC to the SPL to carry out the further scientific analysis. So I was fortunate, I am very grateful and fortunate enough to receive that data of the experiment. And then from there, I started conducting my spectral analysis of the data. So here is simply in this animation, you will see the projection of the geometries as you look from the north pole of the ecliptic plane. In this case, you can see how the conjunction was happening. There was a mom and the Earth, and the green dotted line shows the projection of the radio signal as it was transmitting. So because of the relative geometries, we were able to probe the coronal region as close as 5 solar radii. So here are some specification of the experiment. It was a single downlink S-band. It was a signal frequency in which the mom spacecraft used to communicate. The receiver was at IDS in Bangalore. Frequency Doppler sampling rate was 1 Hertz, and the experiment was conducted in the closed loop. It was a one-way RO experiment. Now, another thing which makes our interpretation of scientific results interesting is what were the solar conditions during May and June 2015. So here you can see that it was near maxima and actually the descending phase of the solar cycle 24. With this information, we analyze our data. Here to explain you the geometry of how the conjunction looks like as viewed from the Earth plane, the sky plane of the Earth. You can see that the dot shows the projections of the radio signal across the sky plane, and with there was the experiment was conducted approximately when the closest path of the ray so here are the projections of the closest point of the radio ray path from the coronal surface. So we were able to conduct the experiments till as close as 4 RS. After that, the window, because it is actually dangerous to quite point at your antennas directly towards the sun, there was a pause of when there was a total blackout, and after that, when mom again reappeared from behind the solar limb, two more experiments were again conducted. Okay, so how do we analyze the data which is received? And how do we try to find out the turbulence regime and what does they explain is here. So we take the Doppler shift. The Doppler there is a transmitted frequency f naught, and we assume that if there is only the range rate Doppler, if it is passing through a vacuum medium and only there is a relative velocities between the spacecraft and the receiver, there will be a assumed Doppler, which is known as a theoretical Doppler. Now, what we observed is little bit different from experimental Doppler, has a little bit difference from the theoretical Doppler. This Doppler and this frequency residual is the one which carries the signature of the solar wind turbulence. And when you do the spectral analysis of those frequency turbulence, you can actually find the turbulence spectrum of the frequency fluctuations. Now, it is assumed that these turbulence in the frequency fluctuations are arising as the result of the fluctuations in the refractive index, which is happening because of the fluctuations in the density of the medium. In this way, we can study the regions of the turbulence spectrum, which is actually at the closest point of the solar, at the closest point or the solar offset distance of that radio ray path. And different days of experiment, as I showed, will correspond to the different heliocentric distances. Okay, so here I have shown you the two different days or two different heliocentric distances of the proximate ray path and the turbulence spectrum corresponding to those days. So here you can see I'll start with the figure B. You can see when there was, our radio ray path was closer to the sun. It was only 5 RS. That time turbulence spectrum were having a flatter slope. And when it was further away and such that it was near 20 RS, the turbulence spectrum were having a steeper slope. I'll just go back a little to give a little bit introduction about how does the Kolmogorov turbulence model work. So Kolmogorov turbulence says that there are three kind of region in the turbulence, such that there is a source region. Whenever you are in the source region of a turbulence, the injection of energy happens and the turbulence has not quite set yet. As you move away from the source region, the velocities of the particle increases. Now, to study this, you can just take an example of some chimney or some flow from the water from the tap. You see, when you open the tap to a certain distance, the flow is streamlined. After that, the turbulence set up. In the similar way, as you are moving away from the sun and for a few solar distances, it is still the source region where the energy is getting injected into the medium. After that, the turbulence is established, and the turbulence established in the MHD waves, and they will create the fluctuations in the density of the medium, and you will see the slope is taking the format of the Kolmogorov turbulence spectrum. Okay, so the different, as we were moving away from the sun, our radio ray path was at the different heliocentric distances, we could see the change in the slope of our turbulence spectrum. So when we correlated our results, our observations of the turbulence spectrum to the theory of solar wind turbulence model as it is given by the theory which is given in the literature, we found out that near the closer heliocentric distances, our slope of our turbulence spectrum was smaller. That means there was the slope was steeper and the turbulence was underdeveloped. As we were moving at the as we were moving at the farther heliocentric distances, the spectrum was also getting steeper and the slope of the turbulence spectrum was increasing. So this was the indicative of developed Kolmogorov type turbulence spectrum. Now, when we correlated our results with the theory, the inference which popped out was that solar wind, when it originates near the solar corona, is subsonic, and that's why, and also because of that, the turbulence is also underdeveloped. Now, as it moves away, it gets accelerated, and in the transition region, due to the developed turbulence which is established in the magnetohydrodynamic waves, and because of its dissipation of the further waves, the temperature of the corona increases. As inferred from the change in the slope of turbulence spectrum, the solar wind particles start getting accelerated, and there comes a region beyond the transition region when flow becomes supersonic and supra-Alfvénic, and with this the particle continues like that in the interplanetary space. Then this Now, what we did was we tried to see the similar experiments have been done by the various spacecraft previously during their own solar conjunction events, and then we decided to track uh, what kind of observations were there in their spectral indexes values. In this case, we are presenting the values from the three spacecraft which conducted the solar experiments during the phase of the solar cycle was same near maxima, but those were the different solar cycles. So as you can see in the mom, when mom did its experiment, there was a signature that the turbulence spectrum was getting turbulence, the change in the slope of turbulence spectrum was happening at the smaller heliocentric distances. This could indicate, one of the indication was that there is a paucity, or there are less abundant active regions in, or the source regions on the solar surface, could pump energy into the coronal region. As you can see, so for the mom, the turbulence was appearing to develop at the closer heliocentric distances, whereas for other spacecraft, it took longer heliocentric distances to the turbulence to get established, which indicated that maybe this might be an indication or insight into the study, the peculiar feeble maxima of solar cycle 24. So all of these results are already published in a paper. It was published last year, and interesting people can look through the paper, and everything is explained in a proper detail, including the data, how the data was, and how the data analysis was done, and how the scientific results were established. So I'll just quickly, this is the first study, and I'll quickly give it the summary why this was such an important study, especially for me and for the Indian space community. This was the first study that utilized radio sounding data provided by an Indian spacecraft to study the coronal dynamics. And this was a really daunting mission, which was taken up by the ISTRAC and the ISRO in 2015, that let's point our antennas and let's try to conduct this solar coronal radio sounding experiment with MOM spacecraft, which itself was a technology demonstration mission and a quite successful mission. So the finding is consistent with the theoretical models, as I have explained, how the models of solar wind and turbulence explain the changes in the turbulence regimes. This also helped us to substantiate the process of heating of solar corona and the solar wind acceleration and its transitions from sub-Alfvénic to supersonic and super-Alfvénic in the near sun region. Now, a very important and interesting aspect of this study was during the same time when our study was published, during that same time, there was some in-situ measurements of solar corona that were conducted by the Parker probe, and they also kind of found out these change in the turbulence regime. Although they found out these change in the turbulence regime of near this solar coronal and solar coronal region, that is and they also established a similar kind of observations as we were able to find out in our study. Although there was some difference because of the observations were conducted at the different phases of solar cycle, but overall the underlying theory and the finding was consistent with the theoretical models as well as the observations, with a very simple technique which was done using the planetary mission. So if I have managed to take up your managed to keep up your interest, so you can check this paper which was published last year, and also this work got featured as the ISRO story of the week, in which the summary of the paper was given, and it is a quite interesting read if you people are interested. So now I will move on to the next part. So there is another mission which is currently around Venus, and it has been sent by the Jaxa, the Japanese space agency. This is a mission which is primarily to study the Venus climate, and it is currently in orbit. So similar kind of experiment was proposed by the Jaxa team. There is a MOU between the Jaxa and the ISRO team. Similar experiment was proposed by the Jaxa team to conduct the coronal radio sounding experiment whenever a Venus Sun and Earth conjunction is happening. So one such conjunction happened in 2021, and there was an experiment which was conducted for the coronal radio sounding experiment. Here I have listed some specifications. The signal frequency was downlink X band. It is the same band in which the VCO communicates. And the period was March 2021. The signal were received at the two ground stations, IDS and simultaneously at the UDSC. The experiment was conducted in open loop. The data was in RDF file format. And this interestingly, so now you can see that 2021, this was the ascending phase of solar cycle 25. And it was near minima phase of the solar cycle 25. So I have used the signals which were recorded by IDS and team and to study the similar study which we did before regarding the turbulence region and the flow speeds. So using the same technique of taking the Doppler and taking the frequency spectrum, here I am presenting the result of what were the turbulence regions which were observed during the Venus experiments, during the VCO conjunction experiment. So in this case, we observed that although the heliocentric distances were changing, the turbulence spectrum slopes were quite they were not, the expectation was the spectrum were always flatter. They were nearly flatter with even with respect to the changing of the slopes, changing of the heliocentric distances. The slopes were near flatter. So this was very interesting. This observation was quite interesting. What we did was we tried to compare it with the spectrum index values in the same inner middle coronal region from different radio sounding experiment. So the experiment which was conducted during solar maxima, there was a transition which was seen in the slope. And during this, in a particular case, when this experiment was conducted during a solar minimum, when Akatsuki conducted the similar experiment, the transition did not happen even at till like 8 or 9 RS. In this case, because of the limitations of the spacecraft and the experimenting, we don't have observations for larger heliocentric distances. Our observations were from 4 to 9 RS. So with this thing, we thought that we will do further analysis. And one advantage we had was, to this time for Akatsuki data, we could use, as we were able to receive a lot of interesting raw data, and the data quality was able to do data quality enabled us to go one step further to actually do the flow speed estimation using the similar kind of model, isotropic quasi-static turbulence model. And here we found out that okay, so this model assumes that whatever turbulence is happening in the solar wind, it is frozen, and it propagates, the turbulence and everything is frozen in that plasma probe, and it propagates outward the sun with the solar wind velocity. It's just like whenever there is a river, and for example, there is a leaf in the river, the leaf, if you have to find the velocity of the river, you try to find the velocity of the leaf which is flowing with the river, and from there you can infer the velocity of the water in the river as well. So this is a very interesting method which is used to actually estimate the solar wind flow speeds near the sun. In this case, we use this particular model which is termed as Efimov-Armand isotropic turbulent model, and it was also developed by the few of the solar groups have developed this mathematical equations in which we use our slope values of turbulence spectrum to along with the radio wave propagation formulation to estimate the solar wind speeds. The details of this method and everything is given in the paper, which you can consult later. So I'll just here I'll share the results. So in our results, we found out that the solar wind velocities were in the range of 220 to 550 approximately kilometer per second in 4 to 13 RS. So going with the usual assumptions, when the speeds are calculated, this range was quite little bit higher than the expected values or the reported values from the coronagraphic observation of the solar wind speeds. So if I summarize results so far, in our study, we found that there was a flatter turbulence consistently as opposed to the expected increase in the slope. Flow speed estimates were also little bit higher than what are usually expected in the inner and the middle corona. So now finally we decided to corroborate our results with the EUV images to actually observe what might be happening in that region, in the solar proximate point of our radio ray path, from where our radio ray path was coming, what might be happening. So here here we observe, here is the interesting observations. Now in the figure in which you can see these black dots, they denote the solar proximate point of our radio ray path as seen from the space of sky. Now you can see that mostly radio ray path were passing closer to the southern helio latitudes. And during that time, there was a large patch of coronal hole which appeared in the southern helio latitudes, and also it was co-rotating along the same time when our experiment was being conducted. So during the entire duration of our experiment, our radio ray path was embedded under the stream of high solar wind flow, which might be propagating, which might be emanating from these coronal holes, and with the coronal holes and the open magnetic field lines. And that might be one of the reason why we are getting consistently flatter turbulence slopes, because flatter turbulence indicates the underdeveloped turbulence. And for the as you can see, if the flow is happening along the open field lines and it is less turbulent and it is more streamlined, so there might be one of the indication why this turbulence was flatter turbulence. And another indication was the high flow velocities which we were getting as a result of our theoretical formulation. So when these three things were clubbed together, this came out this became a very interesting work to actually study the flatter turbulence, to actually study the acceleration of past solar winds without having even with the absence of the in-situ measurements, a very indirect and a very simple and ingenious way to observe the acceleration of past solar wind, that too in the region of inner and middle corona, which is relatively least explored. So this was one of the interesting the significance of this work. And now I am nearly at the end of my talk formally, like we'll take up the questions. So here I'll quickly give the summary. I tried to explain the corona brief introduction to corona, solar wind, and what is the Alfvénic surfaces, and solar wind generation and acceleration of the solar wind particles in the region of inner and middle corona. What is the introduction and the basic principles of the coronal radio sounding techniques, and how does the turbulence and the dynamics depend on the different phases of the solar activity cycle, different appearance of the coronal features, and relative prevalence of the active regions. So just concluding my work, and just want to conclude my work. What is the significance of studying the solar coronal dynamics? It may give answers to the problems such as coronal heating problem and energy dissipation in the least probed inner and middle coronal region, which can further help us to study how solar wind generate and accelerate, what derive some transient events also. For example, if we are lucky, if we are conducting our solar conjunction experiment or this solar radio sounding experiment such that we are able to capture some kind of transient event. A few of the experiments, few studies are already there in the literature where Akatsuki team has actually studied a proper structure of a CME with this radio sounding technique, the similar kind of technique. And we can also use these results for the prediction of the next solar activity cycle. And as you know, the solar wind, these radio signals, they travel to the earth in 8 minutes, and the particles arrive at the lag of few days. So with a further study, there is just a projection that this might help us to improve our space weather models and a lot of things. So with this, I'm just concluding my talk. So the work which we did with MOM was a very interesting and a very daunting work, and I'm very grateful for ISRO to give me this opportunities. Our work was also published it came in a lot of journals and English and vernaculars. And if you people are interested to know more about it, I would request everybody to go and look at this and understand the various aspects of the solar physics. We try to put it up in the simple languages. And so thank you everyone for your attention. And you can also drop me an email and be in contact on other social media platforms. So thank you, Anders. And thank you, everyone.
Any questions for Richa? Is Debish?
Yeah, you can hear me, right?
Yeah, I can hear you.
Yeah, very nice work, Richa. Very nice work. Yeah, I just want to ask that, like, in your plots where you like shown the FFT actually, fast Fourier
Mhm.
transform. So I can see some breaks in the spectra. Could you please explain that? Why is that the breaks are there? Like the at some point the spectra, which is basically straight line, after
Mhm.
some frequency it actually goes up and it goes
Yeah,
down.
yeah,
Something like this. Could you please
exactly. So
explain
this kind of breaks, this
that?
break
Yeah,
you
yeah.
might be yes, yes.
Yes.
So basically, so what happens in this spectrum? We are not concluding this part. This might be this higher frequency thing. They might be the cause of the system noises. So how do we define our data? Is like we take, we put our slope. We consider our slope. The lower boundary is defined as 1/10 of the Nyquist frequency because we assume that above these frequencies system noise dominate. And if our sample rate is one particular value, 1 hertz, so above that we assume that everything is system noise. Sometimes because of the system noise and everything, this kind of kink is usually observed in the turbulence spectrum, like FFTs.
Mhm. Okay, okay. So it's basically coming from the system actually.
Noises, yeah. So that's why we
System.
don't put our slope in that region. We take 1/10 of the Nyquist frequency, and Nyquist frequency is half of our sample rate. Sample rate is 1 hertz. So in every 1 second, we are getting one sample, one frequency value.
Okay. Yeah, because I was assuming like after the uh, Kolmogorov range, you can
Hmm.
have a break, which is
Yeah,
basically a kind
dissipation
of,
rate.
yeah, exactly, but
Yes.
steeper break. So it
Yeah,
can
actually,
the
that's a very good
viscous region, I would say
observation.
viscous, yeah. Mhm.
So to go for the dissipation range, it will
Dissipation
be
region.
interesting if we have a higher sample rate, so that
Yes.
our we can assume that our Nyquist frequency is higher, and we can actually confidently put slopes near the higher things. And there has been already a paper in which their sample rate. It all depends how like how
The cadence of the
like
data, I would say.
yes, how do you collect the
How
data?
much? Okay,
So
okay.
there is some spacecraft, Galileo, some paper is there in which they actually try to go to the dissipation regions also.
Okay, okay. Yeah. Very nice, very nice, sir. Thank you.
Thank
Yeah.
you so much.
We have questions in chat. Ketki, do you want to ask anything?
Yes, I want, first of all, thanks for very interesting talk. I'm curious to know about the comparison between the Parker solar probe observations, or because they are in situ observations, right? And
Yes.
you did the remote sensing observations. So I think with this Japanese instrument, you did the experiment in 2021. So do you have any direct comparison of those time period? Because you said for with mom, but not with the Japanese instrument.
Exactly. So what happened with the Japanese thing was their conjunction geometry was such that we were able to probe from 4 to 9 RS. It depends on the decision taken by the team, how they want to conduct the experiment. So if you can see, I'll show you the conjunction geometry was such that we were able to probe from like this from in the closest was some 3 to 4 5 rs and farthest was 9 rs, and the Parker probe it went till 18 rs, like they have the result published till 18 rs in 2021. Its closest approach was near about 18. So there is no direct correlation. If we would have conducted our experiments for the little bit larger heliocentric distances, then we could see some kind of correlation. So far we
Okay.
are only limited with this thing, and we can like use the projections and everything, but
Okay.
direct observations. Yeah.
Okay. Yeah. Also, one more question. I think I missed it, but in the spectral index plots, you have this dotted line. What does that represent?
Oh, yes, the dotted line is at 0.66, which basically represents the transition from to Kolmogorov regime.
Okay.
Kolmogorov regime is there where turbulence is established.
Mm-hmm.
So, yeah, that is the transition we take.
Okay.
Below it, it is considered the turbulence still underdeveloped. And when you start seeing in any turbulence spectrum, when you start seeing this slope or above that, that means the turbulence is fully established and the energy dissipation has started happening. There is an energy cascade of higher wavelengths to the lower wavelengths, which will further go till the dissipation regime, and the energy will be dissipated in the medium. Here, the
Yeah.
medium being the coronal medium, which will increase its temperature.
So do you expect like after this 22.5 solar radii, the turbulence will be almost at the same level?
Yes, this is what the assumption, like it is established, so the slopes will they will just be asymptote values will reach.
Okay, thank you.
Before Devish, does this answer Chitradeep's question? Chitradeep was also asking about Kolmogorov spectrum index,
Yeah,
the physical implication of the deviation in the indices.
in the physical
Chitradeep?
implication of the deviation in the indices in measured turbulence with that of theoretical, yes. So I could not understand the second part, but the physical implication is this only. So when we reach the Kolmogorov slope, we assume that the turbulence is established, cascade has set up, and energy dissipation is happening. It is that time when the this dissipated energy will go in the medium, and the turbulence, it will help to accelerate the particle, and that will be actually the transition region where the flow become from subsonic and sub-Alfvénic to supersonic and super-Alfvénic. And if we take this analysis further, we can say that that might also be the boundary of our Alfvénic surface. But I have not seen any, I still have to look for the literature for the Alfvénic surface part. But yes, this kind of this transition in the slope indicates the transition in the solar wind flow. So I think there was one more question. Is there a plan of such experiment instrument for Venus mission of ISRO? It is by Ritesh. So actually, yeah. Okay. So yeah, Venus mission is already announced, and some group like our solar group has proposed that whenever such kind of conjunction experiments is happening, it will be good if they could conduct the experiment. So this is already we have proposed, and let's see if the team takes it up. Such kind of experiment can be conducted with Indian mission also, whenever there is a solar conjunction event. So
Devish?
Devesh,
Yeah, so I just want to add one thing. So you have looked into Kolmogorov spectra, which is very important and interesting, but you can also look into Krishnan spectra, because some of the authors claim that the smaller fluctuations, especially in the magnetic field, they follow Krishnan spectra, which has a slope of -1.5, not 5/3. So
yeah.
so you can also
There,
look into this.
yeah, I will definitely, because I also came across this thing in the literature. So I'm not an expert in the turbulence, so I just read about it and I thought there's something about Krashen stick to assumes 2D turbulence and Kolmogorov assumes three-dimensional isotropic turbulence. Some differences there. I'm not sure. I'll have to read about it. But thank you
But
for the suggestion.
yeah. You can look
Sneha?
into that. Yeah. Yes.
Yeah, I
Hi,
will look at
Richa. Thank you so much
Thanks.
for a
Thank
very
you.
nice talk. I
Thank
have
you.
a lookout kind of a question. Like
Yes,
this method of acquiring data, it's very much dependent on how much like densely populated the planetary or other mission satellites are. So
yes.
so then the data will be sporadic basically. So whenever the what is it occultation? Whenever the
A conjunction happens.
conjunction
Yeah.
happens, only
Yes.
then can we have this data basically.
Yes.
So the question is, will there be a time when we'll have a periodic data, when there will be several instruments in like observing different planets or phenomena out there, and like, or do you see this as just one time or like random time experiment?
I actually this is a very interesting lookout question. So I hope that this experiment continues. For example, for MOM, this window for as Mars and Earth have a relative orbital period of 2 years. So with Mars, this opportunity arises every 2 years. So they conducted experiments in 2015, and then
The
2017
latest
and
one was
19.
2021. You showed
Yeah.
that, yes.
Last experiment was conducted in 2021. So there was a little bit data. We are still looking if we could extract science out of it. And Venus, this Akatsuki Venus conjunction happens every 19 months. So
Okay.
they have their frequency of data is quite large. So they have already published some interesting papers from the 2017 data, 2019 data, 2021 data. This is the recent publication on 2019 data, and we also have a interesting, very interesting work in October 2022, which hopefully we'll share soon. But yeah, that's true. This is dependent on the conjunctions and the abundance of the spacecraft and everything, which is so maybe if there's some dedicated solar mission, something like that, we could get more data.
So, like, would you prefer this over PSP and solar orbiter, or this is more trustworthy in your opinion?
In my opinion, I would say obviously in-situ
In situ
measurements are
measurement is,
always,
yes,
yeah,
yes.
it's better to go and actually they are more obviously daunting and trustworthy.
Yeah. Thank you so
We have
much.
a couple more questions in the chat. Dibyakirti Mishra wants to know, is there any explanation behind the transition from subsonic to supersonic during solar maximum and not in solar minimum phase? Is it because of the data limitation or something else?
Actually, it's because of the big coronal hole which was sitting during our entire observation period. So then when we were not able to observe the like what we were expecting, the turbulence should happen near around like 10 or like around, it started happening from 8 RS. Then we observed this is just a natural phenomena which happened, which coincided with our period of study, that there was also a big coronal hole sitting during that time. And because of that, we were getting all of these interesting results like high flow speeds and flatter turbulences. And our relative geometry, like relative geometry of Venus and Akatsuki spacecraft and the ground station at the Earth was such that the radio ray was cruising like very close to the southern heliocentric distance. Southern heliolatitudes. As you can see from the sky projection of these radio rays. So yes, coronal hole was the reason.
Okay. One more from Hari. Did you measure the solar wind speed from your measurements?
Yes, solar wind speed. Actually, we use the observations were of the turbulence spectrum. From there, we extracted the slope values, and then we use some formulation of radio wave propagation along turbulence medium formulation, and then we plugged in our observed values and few more assumptions we take from other empirical equations, and then we measured. Like the method is given in the paper, so yeah, you can go and if there's more interesting thing.
Okay, then he has a follow-up question to that. How did the solar wind speed compare with IPS measurements from elsewhere?
Okay, so actually we have not actively reported the comparison, but we just looked through the literature that if for these 4 to 9 RS, if this is there, what are the approximate value of the solar wind speeds? So our solar wind speeds, our observed solar wind speeds were relatively higher. Then so our solar wind speeds were higher, but then we have to look out for two factors in this case. The IPS measurements, their solar proximate point might be closer to the low and the equatorial heliolatitudes. So low and the equatorial heliolatitudes are mostly like they are the regions of streamer regions, and slow wind mostly arises from the low and equatorial heliolatitude. And in our case, the flow was mostly like embedded in the high speed flow stream. So maybe the values were a little bit higher than the previously reported values for IPS. So we were, so when we try to compare, we had to look out to make the comparison equal, like we had to look for the phase of the solar cycle and the heliolatitude from which the radio approximate point was recorded, was reported. So that's why. No, we have not done that, but it's a very interesting suggestion. So he's saying that measurements on the same days, but dedicated IPS station. So we have not done that. It will require some kind of collaboration and everything, but it's a very good suggestion. We can look up to that.
Okay, another question is, could you please explain how you receive radio signal from MOM and how you identified that signal is coming from the inner middle corona or outer corona?
Yes, that inner middle corona or outer corona, because we assume that we as you can see from this radio signal, we have we know the trajectories. We know the trajectories of the MOM spacecrafts and the ground stations. They are all recorded by the ground station teams every time. The position and velocity of the spacecraft are recorded every time. And with that, we use our geometrical, there is a module known as NASA SPICE module, in which if you plug in the values of the velocities in the flow, they will give you the region from your radio ray path has traveled. So that's how we know that if we projected on the sky, we did some when we projected it on the sky, those values, and we could find out that the region which our radio ray path was cruising through was near inner and middle radio coronal. So it was a result from the NASA SPICE module. I think I have shown one animation also. Trying to change my slides. And what is another question? Yes, like I really try to validate my results. It's an interesting suggestion. What are uncertainties in the measurements? Yes, the uncertainties in the measurements we have taken, they arise, mostly uncertainties have arrived from when we fit the slope. So when we fit the slope, so there is uncertainty in the standard deviation of the slope values, and also the uncertainties in the model. The slope values is the one parameter which goes in the model. There are some model basically is just the set of some equations. There are some other parameters also which goes into the equation, such as outer scale of turbulence and everything. Those are taken from those I have took from the literature in which they are empirically reported. So they also have their own error bars. So all of these things, there was a error analysis, like propagation of error, and then that's how we calculate the uncertainties.
Okay, I think we are done with the questions. Sanjay had asked about origin of slow solar wind and fast solar wind. I think that is not in purview of today's talk, so
yeah,
we can stop here.
Maybe we can slow and fast. You can look up the literature and some good solar
Yes,
physics
yes.
books.
Okay.